So for this next section, we're going to be breaking it up into two parts. The first part will be on a vertical shift, and the next part will be on a horizontal shift. But before I start that, I do want to take a look at these three graphs. This first graph was the one that we started with at the very beginning of the last unit. The second one was the one that kind of came up in the middle of the last section. And then this was one of the problems. I just want you to compare all three. The way I graphed these before, it looked like they all kind of were the same graph, but when we put them all on one plane, you'll see that there's a very big difference. So let me go to Desmos.com. I'm going to enter those three. This was sine x. Here was cosine x. Now 1/2 cosine 3x is going to look really different from the other two. And you can see how much different it is. The green 1/2 cosine 3x really doesn't seem like it's the red curve. And the reason I say that is because you'll notice that this max happens at the y-axis, whereas the red curve's max happens a little bit over, about 90 degrees, or pi over 2 radians. So I'm going to take out the red curve. Hopefully you can see that the max value was decreased by 1/2, so it was a vertical shrink, and the 3x causes this graph to oscillate 3 times as fast as it did in one period. So if we just look at this domain, you can see here that in the blue there was one oscillation. In the green, here was one oscillation, then a second oscillation, and then the third one here. So the 3x causes the cosine graph to oscillate 3 times as fast. And I hope that just puts a general idea of what those graphs were doing when we were graphing them the last time. Getting back into our section, thank you for listening to that first part. We're going to look at f of x equals x cubed, and just as a review, g of x is equal to x cubed minus 3. If you could go in and raise your hand and tell me what the minus 3 does. I'm going to laugh if you actually raise your hand because no one can see you except for you, so that would be funny if you did that. The minus 3 for this graph drops f of x down 3 units. You have learned this as the vertical shift. If there was a plus 3 for g of x, that means that the graph would shift up 3 units. We're going to be applying this to our sine and cosine graphs. So without further ado, here was what your equations are in the cat packet. You have y equals a times sine of bx plus d, or you could have that last constant come in the front to have y equals d plus a times the sine of bx. And again, all this is doing is shifting the graph of sine or cosine up, or it might shift the graph down. And as a reminder, you have seen this before in your in Unit 2. So this is really where Unit 2 is going to come into play now. The vertical shift will be quantified by that value of whatever d is. Please keep in mind that everything is also fair game still, in the sense that you will still be required to look at your amplitude, and you're also still going to be required to look at the period. So the period may change, the amplitude may change, the intervals will most likely change again depending on what's inside the function, and then now we're also going to add a vertical shift. So let's go and start this problem first, and then the next problem I'm going to have you try afterward, and then we'll check it. This one we'll do together though. Y equals 1 minus sine of 2x. I'll start the way I did before. The amplitude is going to be the number that's in front of the sine, not the 1 minus, but this one in orange will be the amplitude. So the absolute value of that 1 is just 1. The period is going to be 2 pi divided by 2 to be that b value, and we get pi. The intervals are going to be the period divided by 4. So our intervals will be in pi over 4. I also want to note that we do have a negative here, which will cause that sine function to just flip around. Our vertical shift will be the 1. So let's go and put all this information together. And I believe it does ask us to graph 2 periods of it, so we'll do both positive and negative. Now the amplitude was 1, but here's the difference now. The vertical shift means that we actually are going to go up 1 unit. So my highest max value for sine is going to be at 2. My lowest sine value will be at 0. The 1 actually is going to be that line that cuts the graph right in half down the middle. So if you want, I'm going to make this dashed line because that's essentially going to be my new x-axis. Now let me go and list the intervals. We're going to go in pi over 4s, so I'll label this point as pi over 4. Here is 2 pi over 4, which is also known as pi over 2, 3 pi over 4, 4 pi over 4, which is going to be known as pi. Same thing on the left. Sine function always starts at the origin, but this time keep in mind because of the vertical shift, the origin is not actually going to be at 0, 0 for this function. Because we shifted it up 1, we're really going to start at 1. Usually when I go to the right, the sine function will go up, but because I have this negative here, I'm going to have to make sure that instead of going up, I'm going to go the opposite direction and go back down. So at pi over 4, the y value is going to be 0. At pi over 2, we'll go back up to our new x-axis, which will be at 1. The y value will be 1. At 3 pi over 4, we'll do a value of y value of 2. And at pi, our sine value will have a value of 1. Going back the other way, at negative pi over 4, at negative pi over 2, at negative 3 pi over 4, and there you go. So it does look like our sine function that we worked with before, but it was shifted up. That's the only difference that we're adding here. And those are your 2 periods of 1 minus 1 sine 2x. Now, a good question that could arise here is, how do I know if I have the right graph? Because when you shift it up 1, it's now a little bit different and you're not really that sure. Possibly. So what we could do is we could plug in a number like pi over 4, and if I did y of pi over 4, I should get out a y value of 0. So let's see if that's true. We have 1 minus 1 times sine of 2 pi, 2 times pi over 4. And if we simplify this, we get 1 minus 1 times the sine of 2 times pi over 4 is going to simplify to pi over 2. On the unit circle, sine of pi over 2 is 1, which means I get 1 minus 1, which is indeed 0. So I have a coordinate here of pi over 4, comma, 0, which is exactly what I have here. And I can check that for multiple points in case I'm not sure if the graph that I graphed is the correct one. What you're going to do next is you're going to go ahead and graph 2 cosine pi x minus 3. Keep in mind that this is going to be the cosine function, which means that your starting point will not necessarily be at the origin, but it will start out at its max or min. Go ahead and pause the video and then resume once you think you have the answer. Okay, we'll start this problem off exactly the way that we did before. The amplitude is going to be the absolute value of 2, which is 2. The period is going to be 2 pi divided by b, and b was pi. That simplifies to 2. My intervals will be taking my period, which is 2, and cutting them into 4 pieces, and that's going to be a half, so my intervals will be halves. And my vertical shift is down 3. Combining all this information, my range was starting out from negative 2 to 2 because my amplitude value was 2, but the vertical shift is causing me to go down 3. So let me back up here just to clear something up. When I'm graphing, my amplitude is going to be first. My vertical shift will be applied afterwards. So the vertical shift down 3 is now going to take out this 2, and I'm going to do a 2 minus 3, and that's going to get me to a negative 1, because I'm literally shifting the y values down 3 units. This negative 2 is going to be shifted down 3 units, and I'm going to have a negative 5 for my new y value. The midline, the line that's going to cut the graph right down the middle, looks like it's going to be right at negative 3. And this will be my new x-axis. So usually I have my points going through the x-axis, but this time they're going to be a little bit different. Okay, I'll go ahead and label the intervals now. The interval will be a half, and 1, and 1.5, and 2. I'll go back in the other direction because we are looking for 2 intervals. And now, cosine. Sine, I would usually start right where this new x-axis would be. Instead, though, cosine starts at its max at -3. Now, I am going to start at its max this time of -1 because the value of 2 is positive here. If the value of 2 is negative, I would be actually starting at my min because the cosine graph would be flipped upside down. So with that said, we'll start our max for cosine at -1. At a half, we'll go back down to y equals -3. At 1, the minimum value will be -5. And then at 2 will be 1 complete period for the function, which means that we'll be back at our max of -1. Same thing on this side. We'll just flip-flop the values, and then we'll connect the dots. And this is going to be the graph of y equals 2 cosine pi x minus 3. And as always, on your own time, if you'd like to check these answers to see how they compare with cosine of x, you're more than welcome to. And if you would like to check these values of a half or 1 or 1.5 or 2 and see if the y values really do check out to those numbers, please do so. It would be a good exercise for you and your unit circle application. That's it for this video. Thanks for watching.